Welcome back to Chapter 10 of America's Boating Club's Sail Course. In this chapter, we will be covering sail shape. The wind on the sails is a combination of boat speed and wind velocity. And the airflow that's going around the sail is what develops the forces of it. So if we look at our diagram over here, it's as the air moves across the sail, there becomes a high pressure area on the windward side and a low pressure area on the leeward side, the downwind side. Each one of these little arrows represents the amount of pressure that's being generated by the wind in that direction. And so we see the forces are much stronger at the front and very, get less on the back side. What we do is we add all these forces together, and that gets us to the force on at this point here, which is essentially our center of effort for that sail. Here's another illustration for the effect that airflow has on the sails. So as our airflow goes around the sail, it develops lift. It's the difference of the wind speed on each side of the sail that creates that pressure. The wind velocity is higher on the leeward side, that's this one over here, and on the windward side, we've got it's a little slower and it has higher pressure. This pressure difference is what actually creates our lift, which is our force that propels the boat. This force is really important as we look at the way it varies. So for example, our force gets stronger based upon the square of the wind velocity. So if the wind goes from 2 to 4, it's not just 2 points difference, it's actually the square of the difference, which is, larger. The terms chord and draft are also very important for us to understand. So let's look down here. Our chord is our line from the front of the sail to the back of the sail. And our draft is this area here from the chord line up, it's the maximum area to the sail. So in here would be our maximum point of draft. That's our draft of the sail. In this case here, I'm going to try and demonstrate the effect that wind blowing across the sail causes and generates lift. So watch what happens to this sheet of paper as I blow on it. That's essentially the lift that's created by the moving air. The aerodynamic lift is energy derived from the wind passing over the sail. The angle of attack is the angle between the chord line and the apparent wind. So here's our chord line running from the front to the back of the sail, and here's our angle of apparent wind. This angle here is our angle of attack. The angle of attack between the apparent wind and the sail chord line determines the sail's ability to generate force. This angle of attack is the same for all points of sail, except when you're running downwind. For maximum force, the angle of attack should be about the same whether you're close reach or off the wind. It should always be around 20 degrees. As the apparent wind changes, you have to trim your sails differently, or as you change course, you have to trim the sails to maintain that same angle. The angle of attack is the angle between the apparent wind and the chord and is the biggest single variable in determining the forces generated by the sail. Here we have 3 different boats on different headings, but they have all got the same apparent angle of attack, and you can see how the sail is trimmed in. We adjust this angle of attack by controlling the main or jib sheet, and that's what pulls our sails in. We have to continually change our boat heading and apparent wind. So as our heading changes, then we have to trim in the sail to match that different heading that's relative to the apparent wind. Stated another way, As we're going close hauled or beating, going upwind, the sail is pulled in real tight. As we bear away from the wind and we start reaching, we're going to ease the sail out more and more as we bear away from the wind. So in this case, we've bared away from the wind, but our angle of attack, because we let the sail out, is still the same. When we're sailing directly downwind, we no longer get an aerodynamic lift from the sail. Instead, we're just using the wind to push the sail. This is in drag mode. When we're in drag mode, the wind is just simply pushing against the sail and we're getting no lift. And the force is really a function of how much this surface area is, the square footage of the sails as it's being pushed away. This is a very, some people think that when you're going downwind, you're going to be going as fast as you can go, but that's not really the case, as we saw when we were doing our vector analysis. Running downwind is actually very slow, and I think it's my least favorite point of sail, because when we're going downwind, we're going with the wind, and we're actually probably traveling at about the same speed as the wind. So then when you're going downwind, you don't get, for me, it's very hot and boring. So some boats think it's advantageous to actually head up just a little bit in this situation, so that you're no longer just running down and letting the sails be in push mode. You're going to head up and then take advantage of some aerodynamic lift as we go across the wind. When we do that, we'll be sailing a little longer distance, but we think we'll be sailing at a faster rate of speed, which then will get us to our destination quicker. This is especially true in marginal planing conditions. If we go just a little bit faster, we can get the boat up on a plane, and then we can go, make really good progress in the direction we want to go. Some boats are so fast that when they go downwind, that the apparent wind shifts forward so that you never actually have a downwind apparent wind. This would be an example of ice boats or modern America's Cup boats. As they go downwind, they generate speed, and the friction is so little compared to the other factors that the apparent wind actually shifts forward on them, and they're always continually going upwind. An ice boat never goes downwind. It is always feeling the wind going up, apparent wind going upwind. Another way of looking at this is, as when the boats are going fast, would be like when we're driving in our car and the wind is blowing 10 and our car is going 40 miles an hour. You stick your arm out the window, the apparent wind is always going to be in front, no matter what. And so that's the same sort of thing that happens on these very fast boats. Sail efficiency is governed by the ability to keep airflow attached on both sides of the sail over as much of the area as possible. Let's look at this first sail shape as it's trimmed. Here's our angle of attack, which is about 20 degrees, and so the wind is flowing well across both sides of the sail. And so here's the sail, and the wind is not disturbed as it goes by. In this instance here, where we're in a luffing situation, the angle of attack is too narrow, and because the angle of attack is too narrow, we're getting a disturbance of the wind as it goes across the sail. So it's good on this side, but it's getting disturbed on the downwind side. In this case here, we've got too large of an angle of attack, so our trail is trimmed in too tight. So as the air goes by, it starts off attached, but then when it gets over in this area here, it becomes stalled and disturbed. The air on this side of the sail is nicely attached, but when it gets to the end, it's going to fall off also. This is a picture of a sail in a wind tunnel, and the main is over trimmed. And so what we can see is as the wind is coming in, it's staying very tight on here until it gets to the end of the sail, and then it comes around and starts being disturbed. On the downwind side of the sail, the wind never really gets attached. It just starts sailing off to the side. Here's another illustration of a sail in a wind tunnel. If you see these lines here are smoke trails that are put in the wind so we can see what the wind is doing. This is a well-trimmed sail. So as the wind is coming by here, it's staying attached to the sail on the windward side. It's also going around the jib on the outside and staying well attached to the back. In addition, we have some wind going through the slot between the main and the jib, and that compresses it a little bit, and that gives us more power. That's why we like to see why the sails on a sloop are faster, because of this Bernoulli effect in this space here. In this wind tunnel example, the main and the jib are not trimmed together in the same amount. In this case here, we think the jib is a little bit under trimmed, so the slot between the main and the jib is too wide. And what it does is it allows the air to go through the slot, and then it breaks away from the mainsail. And so we have this stalled area on the back of the main. In a previous session, people were wondering, what do we do with all those adjustments that are part of our running rigging? In this slide, we're going to start looking at how we might use some of those tools to adjust the location and the amount of draft in a sail. Now, the draft, you remember, is the depth between the sail and the chord of the sail. The draft is a major factor in determining the amount of lift or the power that we're going to use to drive the sail. The amount of draft is controlled by the outhaul, the amount. The location of the draft is controlled by the halyard and Cunningham tension. If you increase luff tension, that moves the draft forward. We can also affect the draft by bending the mast. More bend moves the draft forward and reduces the amount of draft too. So let's take a look at our first scenario, the average wind. And what we want to do there is try and figure out how do we position that draft where it gives us the power that we want. When we're speaking average wind, we're thinking of the wind in the 8 to 12 knot range. And what we'd like to do is have a fairly large draft and have it be in the front third to front half of the sail, in this space right in here. In this situation, if the sails were old, the draft might have slipped, fallen back, stretched out, sail stretch out, and the draft moves back. So to pull the draft forward, we would increase our halyard tension in Cunningham. In light wind, what we would like to do, this is in the 2 to 8 knot range, we would like to add more power to the sail and move it more to the back a little bit. We're going to let the draft be back a little bit. We want, if it's light wind, we want more power, so we want to get as much out of this as we can. So to get the draft to move back and fuller, we're going to ease the Cunningham or take the pressure off the halyard and also reduce the outhaul a little bit. And that will move our draft back and make it bigger. The third scenario is in strong wind, and that'd be 15 knots or greater. What we want to do is, in this case, the boat is going to become overpowered, and we want to reduce the power. And to reduce power, we're going to reduce the draft and move the draft forward to the front part of the sail. So in other words, in very strong winds, we want to reduce the draft and move the draft forward. In some instances, like when we're sailing on Clinton Lake, in winds that are very light, where the wind is just barely blowing, we might also try to, if we have too much draft in the sail, the wind actually separates from the sail. And so in very light conditions, we might tighten everything up to take the draft out so that the sail does not stall in those conditions. When we're out sailing, we don't have the luxury of having a wind tunnel and the smoke going by to show us where the wind is stalling or breaking away. The flow is becoming unattached. And so when we're out on the water, we've got these little yarns that are on the front part of the sail, the luff of the sail, and these yarns are on both sides, and they give us an indication of what the wind is doing as it's going across the sail. To help us know where the wind is, how the wind is reacting to the sails, we put telltales on the sails. And in this case, we're going to look at some of those telltales and how they are affected. When we're on course, we would have these telltales that would be flowing both smoothly on both sides of the sail. That means that our sail's trimmed so that this wind stays attached to the sail for the whole duration of the path. To achieve this optimal trim, we would have the sail trimmed in so that the yarns are flowing back on both sides. The windward and leeward telltales are streaming back. Now we can do this also by trimming the sail, or the skipper can actually steer the boats so that the telltales are both streaming back. So when you're going close hauled, you would have if this outside one starts fluttering or the inside one fluttering, then the skipper can actually steer the boat to make them turn in the right direction. In the case down here, the sail is trimmed too tight, and we've got our angle of attack is too high, and so that the sail is actually stalled on the leeward side of the boat, and so the yarn is fluttered out. So the way we would solve this problem is we would ease the main sheet, and that would cause the sail to come back around because it's trimmed too tight. In the instance up here, the yarn is fluttering on the inside. And what that means is we are not tight enough. So we can trim this sail in just a little bit, and that would cause the yarns then to go back and flow properly. If you're already in a close hauled position, then the skipper would need to steer the boat down to get it to trim in better. We really rely on the sheets to trim this in and out direction for the most part. They're the big numbers, big things that help us make that happen. And it adjusts our angle of attack so that it's a proper amount of in and out. It also has an effect on twist, so we'll talk on the next slide. There is a tendency for new sailors and experienced sailors to over trim the sail into this kind of a position because it looks good, the boat feels fast, the sail has got a pretty good shape, but if you look at the yarn, what will happen is the boat will feel slow, bogged down. And the maximum that some people use is if the boat feels slow, let the sail out until it starts fluttering on the other direction. So until the inside one, the telltale starts moving. We also have, on my boats, we also have a telltale on the back of the sail up near the top of the batten that also tells us how the wind is exiting off from the sail. And so that gives us another indicator of the trim. Here's a picture of the telltales on the jib and on one of my boats. This is probably my Thistle because it's got a black mast. And we can see that we're looking at two things here. Here's the telltale that's on the luff, and it's flowing back nicely. And we also have the telltale flowing on the leech. And in this case here, you can see that it's streaming back well, and that means we're in pretty good trim. Now, when I'm driving the boat from the skipper station, there's a window somewhere down in this space here where you can actually see through the sail up to monitor this telltale to see whether the jib is stalled or not. The apparent wind is continually changing, and we need to change the sail trim as well as steer often to maximize the apparent wind. Now, if we were trying to go through all the vector analysis in order to figure that out, that would be, it would just be overwhelming. Instead, we have the masthead indicators, or these wind indicators, that help us know what the apparent wind is doing. And this is my example of the masthead that's on the top of one of my boats. And so what we do is it's up there and it's very, very sensitive. So if you just blow on it just a little bit, just a tiny bit of breath of air, it'll react to that change. The masthead indicator also has this V thing too that you can sort of see. And what that helps us know is when we're inside that no-go zone where we're sailing too high into the wind. And I use that frequently to see whether I'm sailing optimally upwind or not. We also, in addition to the masthead flies, we might tie some yarns onto the shrouds, which help us know what the wind is doing at various levels. The shrouds like here, if you look at the cables, they've got yarns here, 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 and here. If you look at my Capri, I've got yarns tied on that thing in every place to kind of help me understand where the wind might be blowing. Those telltales at various places also kind of give us an indication of what the wind is doing at different heights of the boat. So our masthead fly is up here telling us one thing, and we can look at the yarns down lower, and sometimes they are not telling the same story, which then says that the wind is blowing differently up high than down low. Let's look at how aspect ratio affects our sail trim. If you remember, aspect ratio is the ratio of the length of the sail versus the foot of the sail. And so the higher aspect ratio, taller the mast, has a more efficient sail shape, but to counteract that is it is much more complex to get the sail shape to trim up properly with the wind. Let's look at how mast height has an effect on the wind speed. Wind on the deck is slower than wind higher up the mast. This is caused by friction between the sea and the wind, which reduces the wind speed at sea level. Because we have different wind speeds higher up, we need to adjust the sails for these different wind speeds. The optimal trim angle of the sail cord changes with height, and this is called twist. Twist is the change in angles between the sail cords as we go higher up the deck. By putting some twist in the sail, it allows us to adjust the angle of attack due to the wind speed difference with heights. So if we look at the baseline here, this is our deck view, which is 10 feet above the sea level on a 40-foot mast. And so that would be 50 feet up. Now, this difference is greatest when we have light air. So in a very light air day, the wind is reduced to 20% of the wind speed at the height of the sail. And when it's a moderate day, we get, the wind is not affected as much by the friction of the water, and so it's closer together. As the wind gets stronger, the difference between the height of the sail is reduced. So in light air days, we need to put more twist in the sail to allow for this variance. In heavy air days, when we're overpowered, we might also put twist in the sail to spill wind out of the top of the sails, which then would reduce the heeling forces. Let's take a look at a couple laser pictures and see how the twist affects the sail on those boats. In this case over here, we've drawn a straight line down along the sail, and you can see how the sail has actually moved away from that straight line, which would be caused by a tight leech. And so in this case, the sail is twisted more in this section of the sail than down below. In this case here, we would see really probably more of a proper trim of the sail, because as we're twisting it open, the top part of this sail opens up more to accommodate or allow for the twist of the wind. We need to open up the top of the sail to allow for the fact that the wind is blowing stronger up there, which changes the apparent wind at that height. Let's look over our vocabulary for this chapter. The aspect ratio is really just a ratio of the length of the height of the mast to the foot of the mast. Attached flow is what we're trying to achieve by having the wind flow smoothly along the surface on both sides of the sail. A backwind is when we when we over-trim the jib, and that causes the sail then to be over-trimmed and distorts the mainsail. Lift is the force generated on the leeward side of the sail by air passing over the airfoil shape. It's the force that makes the sailboat go. And separation is when we do not have that attached flow and it causes the sail to stall on one side or the other. Stall is the condition when the airfoil is too far away. The airfoil's shape is too far from the proper position, and the wind breaks away and causes the air to be disturbed. This concludes our section on sail shape. In the next section, we'll actually look at what we need to do to prepare to go sailing.